This is a Tomahawk cruise missile. It costs $2 million, flies for over an hour without a pilot, and arrives within 10 feet of a target 1,000 miles away. But distance is not the engineering problem. Keeping a subsonic missile invisible, on course, and thinking for itself across an ocean, that is where things get obsessive. The mission begins not at the launch tube, but in a planning cell that may be thousands of miles from the target. Before a Tomahawk ever lights its engine, a team of targeting specialists builds what the Navy calls a mission data package, a complete digital description of everything the missile will need to know, from the moment it leaves the ship to the moment it hits. This package takes hours to build and contains more navigational information than most commercial aircraft carry for a transatlantic crossing. It includes the entire flight route, broken into waypoints. It includes terrain elevation data for every mile of the planned path. It includes a precise description of what the target looks like from above. And it includes the contingency instructions for what the missile should do if any of those things stop working correctly mid-flight. The Tomahawk is not a dumb weapon pointed in a direction and released. It is a small autonomous aircraft that happens to carry a warhead. Its wingspan, once deployed, stretches to just over 8 feet, about the width of a standard parking space. Its engine, a Williams F107 turbofan, produces roughly 600 pounds of thrust, which sounds like very little until you realize the missile weighs only 2,900 pounds fully loaded and only needs to sustain level flight at around 550 miles per hour. Not win a dogfight. Fuel efficiency matters more than raw power because the mission profile demands endurance. A Tomahawk flying a direct route to a target 1,000 miles away is airborne for roughly 100 minutes. One flying an evasive route around radar coverage zones might be airborne for considerably longer. The first navigation system that activates after launch is the Inertial Navigation Unit. This device contains accelerometers and gyroscopes that measure every movement the missile makes. Acceleration, rotation, change in direction, and integrates those measurements continuously to calculate position. It knows where it started. It knows every force that has acted on it since. From those two facts, it calculates where it must be now. The math is elegant, and the hardware is precise. But inertial navigation has an unavoidable flaw. Error accumulates. A gyroscope that drifts by a fraction of a degree per hour produces a position error that grows with every passing minute. At launch, the inertial system is accurate to within a few feet. An hour into flight, flying on inertial navigation alone, that error could have grown to several hundred feet, enough to miss a hardened target entirely. This is why the Tomahawk does not rely on inertial navigation alone. The first correction system is TERCOM, Terrain Contour Matching. As the missile flies, a radar altimeter beneath the airframe continuously measures the distance between the missile and the ground. This produces a strip of elevation data, a profile of the terrain passing beneath. The mission computer compares this strip against a stored map of the planned route. When the measured terrain matches the stored terrain, the system knows exactly where the missile is, not approximately, not within a margin of error, but precisely to within a matter of feet. The stored maps are derived from satellite imagery and are accurate enough to distinguish a riverbed from a road. TERCOM does not work over flat terrain, which has no distinguishing elevation features, or over open water, which has none at all. This is why Tomahawk flight routes are planned to cross varied terrain wherever possible, and why a missile launched from a ship spends its first minutes in a guidance-limited state, flying on inertial navigation over featureless ocean until it reaches land. Too little terrain variation beneath the missile, and TERCOM finds no match. The missile continues on inertial navigation, error accumulating. Too much reliance on TERCOM over contested airspace, and the radar altimeter's emissions become detectable, giving away the missile's position and altitude to ground-based sensors designed to listen for exactly that signal. The system is designed to use TERCOM corrections at intervals, not continuously, threading a path between navigation accuracy and electromagnetic silence. Throughout all of this, the missile is flying at an altitude that would make most pilots deeply uncomfortable. 60 feet above the ground is the standard cruise altitude for terrain-following phases of the flight. At 550 miles per hour, 60 feet of clearance means the missile is crossing the terrain at a rate where any navigation error, any unexpected obstacle, any deviation from the stored elevation map resolves itself in fractions of a second. The terrain-following algorithm adjusts pitch continuously, climbing for ridgelines and descending into valleys, maintaining that 60-foot band with inputs arriving faster than any human pilot could process them. The GPS receiver activates once the missile clears contested jamming zones or reaches waypoints where the mission planner has authorized its use. Military GPS, the encrypted signal designated PY code, is a different system from the civilian GPS guiding a phone across a city. Civilian GPS is accurate to within roughly 15 feet under good conditions. Military GPS, using the encrypted signal available only to authorized hardware, is accurate to within a few feet under the same conditions. More importantly, it is resistant to spoofing. A spoofing attack feeds a GPS receiver false signals that appear legitimate, and are convincing the receiver it is somewhere it is not. The Tomahawk's receiver cross-checks GPS position against the Inertial navigation system's calculated position. A sudden large discrepancy between the two, the signature of a spoofing attack, triggers the missile to distrust GPS and revert to inertial navigation and TERCOM until the discrepancy resolves. Too aggressive a spoofing signal and the cross-check catches it immediately. Too subtle a spoofing signal and it cannot move the missile's computed position far enough to matter before TERCOM resets the navigation solution at the next terrain match. As the missile approaches the target area, the third and most precise navigation system activates. DSMAC, Digital Scene Matching Area Correlator. The missile's nose contains a small camera. In the final miles of flight, this camera photographs the terrain ahead and compares the image against a reference photograph stored in the mission data package, a satellite image of the target area taken before the mission. The comparison is not pixel by pixel. The algorithm identifies structural features, building outlines, road intersections, distinctive shadows, and matches their spatial relationships against the reference. This process locates the missile's position relative to the target to within a few feet, regardless of any accumulated navigation error from the previous hour of flight. DSMAC is the reason a Tomahawk can fly 1,000 miles using 3 separate navigation systems, each one with its own error characteristics, and still arrive at the target within 10 feet of the planned impact point. The terminal phase of flight requires the missile to transition from cruise altitude to attack geometry. For most targets, this means a steep dive in the final seconds, arriving at an angle that maximizes warhead effect against the structure below. The flight computer calculates the approach angle, adjusts throttle, and reconfigures control surfaces. The entire terminal sequence from DSMAC lock to impact takes under 30 seconds. During those 30 seconds, the missile is descending, accelerating, and continuing to refine its position estimate as the camera image updates with every passing frame. The warhead carried by most operational Tomahawks is the WDU-36. A blast fragmentation design containing approximately 1,000 pounds of PBXN-107 explosive. The fuse can be set for impact detonation, delayed detonation, allowing the warhead to penetrate a structure before detonating inside, or proximity detonation for targets where blast effect matters more than penetration. The fuse selection is made during mission planning and loaded into the mission data package. The missile does not make this decision. It executes the decision that was made hours earlier by the targeting team. What the missile does decide, continuously and autonomously, is how to survive long enough to deliver that warhead. The flight profiles, the specific altitude, the specific route, the specific timing of each navigation mode, is designed around one constraint above all others. The missile must not be detected and engaged before it reaches the target. At 60 feet above the ground, it is below the effective coverage of most ground-based radar systems, and which are designed to track aircraft flying at thousands of feet. Its small radar cross-section, roughly comparable to a large bird, means that even systems capable of looking low struggle to distinguish it from ground clutter. The combination of low altitude, small signature, and varied routing makes the Tomahawk one of the most survivable weapons in the inventory for the threat environments it was designed to penetrate. Everything described so far assumes the mission goes as planned. The data package is accurate, the GPS signal is available, the terrain matches the stored maps. Actual combat operations introduce complications that the missile has to handle without any communication from the operators who launched it. Once a Tomahawk leaves the launch tube, the ship that fired it has no guaranteed ability to communicate with it. The missile is on its own. The Block 4 Tomahawk, the current production variant, introduced a two-way data link that changed this constraint significantly. The data link allows operators to send updated targeting coordinates to the missile in flight, to retarget it against a different aim point, or to redirect it entirely to a different target, while it is already airborne. This capability sounds simple. The engineering behind it is not. The missile must receive the new data, validate it, recalculate a complete flight route from its current position to the new target, assess whether it has sufficient fuel for the new route, and execute the new plan. All while continuing to fly at low altitude through potentially hostile airspace. The recalculation takes seconds. A missile that was 12 minutes from hitting one building can, in those seconds, be redirected to a different building 30 miles away. The data link also allows the missile to transmit imagery back to operators before impact. In the final minutes of flight, as the DSMAC camera is imaging the target area, that imagery can be relayed to decision-makers who can confirm the target looks as expected, or abort the strike if something has changed. A vehicle convoy that was at the target when the mission was planned may have moved. A building may be occupied by people who were not expected to be there. The abort command, if sent, fires a destruct sequence that destroys the missile before impact. The warhead does not detonate. The mission data package, including the stored target imagery, is physically destroyed to prevent recovery. The logistics behind each Tomahawk launch extend well beyond the missile itself. The ship that fires it carries Tomahawks in vertical launch system cells, sealed tubes embedded in the deck, each one holding a single missile in a launch canister. The canister maintains the missile in a controlled environment from the moment it leaves the factory. Temperature, humidity, and vibration are managed inside the canister throughout transit and storage. A Tomahawk that has sat in a launch cell for several years without being fired is still expected to perform identically to one fired the day it arrived. The components with the shortest service lives, primarily the battery systems that power the electronics during launch, are designed to be replaced without removing the missile from its canister. While the cold launch sequence uses a gas generator to eject the missile from the tube before the engine starts. The gas generator fires, building pressure inside the sealed canister, and the missile is pushed upward by that pressure at roughly 40 feet per second, fast enough to clear the deck, slow enough that the launch forces do not damage the airframe. The engine ignites at a safe altitude above the ship. The wings deploy. The tail fins extend. The inertial navigation unit, which has been spinning up for several minutes inside the tube during pre-launch preparation, takes its first position, fix. The missile pitches over toward its initial waypoint, descends toward cruise altitude, and begins flying the route that was loaded into it hours earlier. The entire sequence from launch to first waypoint takes under 2 minutes. For the next hour, the missile flies alone, navigating by the accumulated intelligence of the mission data package, correcting itself against the terrain beneath, cross-checking its position against the satellites above, and making thousands of small flight adjustments every minute to stay on course, stay low, and stay alive. It does not know why it is flying to the target it has been given. It knows only the route, the aim point, and the decision tree loaded into its mission computer. When it arrives, it executes. The ship that launched it will not know the result until imagery arrives from another source. A drone overhead, a satellite pass, a report from the ground. By then, the missile is gone. The missile is gone. The missile